worked quite a lot on interstellar ices, mostly using laboratory experiments. Done quite a lot of work on the interpretation of the ISO results, and we have the origin of the pH's emission interpretation of pHs. So it's going to talk to us today about astrochemistry and astrobiology, which is a topic he's been working on quite a lot in the last few years. And he has some very interesting results to present to us today.
Thank you. Okay, so good afternoon, everybody. So indeed, I'm going to talk about the pre-Baltic relevance of interstellar or pre-cometary ices photochemistry. And actually, the idea is to try to see if there is a bridge between astrochemistry and astrobiology. You know that astrobiology is a very popular, I would say science, but popular in the sense that everybody is talking about astrobiology. But as there is absolutely no evidence for exobiology from the Earth, it's a science which has actually no real object. So, in fact, I must say that I'm going to show you that there is maybe, at least conceptually, I'm not talking totally about experiments, but certainly conceptually a way to pass from astrochemistry to astrobiology. And I would like actually to promote this idea so that we can do the right kind of experiments to see if there is a way to do it. And I will show you that it is certainly possible. Okay, so the idea actually is that you can do a lot of experiments, and this is why my team at the beginning was called experimental astrochemistry. And then the CNOS developed the idea, like NASA actually, that we should include the team origins. So I decided to move to origins and to call my team astrochemistry and origins, and to see if this astrochemistry is indeed at the origin of the chemistry for living systems. So basically, if you compare what you can do in the lab or what you can do in astrophysics, I will just use a limited set of examples. And this is a nice view where you see on the pillar of creations in these molecular clouds. Molecular clouds, there are places where you observe indeed molecules. I would like also to convey the idea that molecules are observed in the gas phase, but they are very, very simple molecules. When in the solid phase, the molecules become suddenly extremely more complicated or complex. And actually, you can simulate this phase. It's extremely difficult to simulate gas phase chemistry, and especially if you look at the evolution of the gas phase, but it is much more easy to simulate solid state chemistry because you can just reproduce what's going on in the lab and going to give you an idea. So that's actually UV microwave discharge lamp. You see that this kind of light, this is actually due to the ionization of hydrogen, and then what you see here is H-alpha, actually. And in fact, that's what you see, actually. But this lamp produces a lot of Lyman alpha, and this Lyman alpha is used to operate photochemistry on gas. Okay. And then this is why I'd like to show this kind of comparison, because it's exactly the same kind of process, at least on the large scale. Okay, so first, before we start, it's good to remember what is the cycle of solid-state matter in the galaxy. When I was starting my PhD, there was even not a mention of the dust in the interstellar medium. You know that, for example, the first molecule in the interstellar medium is H2, and there's no way to form H2 if you don't have the surface. H2 is a homopolar molecule, so when you form H2, you get 4.5 eV of excitation in the molecule, and since there is no way to get rid of it in the gas phase, then the molecule just, the two atoms just rebound and you don't form H2. So actually, you need a surface, and this was shown as early as 1946 by a paper by Knapp, Van Hulst, Meyenberg, and Fortney, by Dutch people. We are extremely advanced in understanding what is needed to do this chemistry in space. So you need this interstellar dust also because H2 is the mother of all molecules. Since as soon as you have H2 in the gas phase, then it reacts with cosmic rays to form H3+, and then H3+ is going to react with the atoms to form molecules. If you don't have, actually, if you don't form H2, you cannot form the other molecule. So in a sense, all the molecules you can see, even in the gas phase, are coming from the grains. Without grains, you don't have any molecule. So what is actually, where does this dust come from? That's quite well known. Essentially, heavy atoms, because I'm going to also talk about elements, because I'm going to give a few guidelines about what kind of chemistry you need to consider if you want to have living systems. And in fact, I want to also convey the idea that the chemistry which is at work in all living systems is probably the only one which can work in the universe. So it's extremely important to understand that the chemistry of carbon and water is probably the only one which will ever give you something which is organic. So you know that elements are not made in the Big Bang, apart from hydrogen and helium. And so the heavy elements will come from supernovae, which enrich the galaxy in heavy elements. But then after that, when you form stars, you have, at the end of the life of the stars, the AGB on the supergiant branch, you will get the ejection of the outer layer of the stars, and you will form dust grains just within this kind of ejections. And it's very peculiar because actually all the conditions are met so that the envelope of the star allows for condensation of elements at a rate which makes, in fact, dust grains, and dust grains are made within these objects, and these dust grains are observed very easily because actually they scatter and diffuse light, and so that's why you see, for example, in molecular cloud, you see very strong absorption due to the fact that you have an enormous surface, a very large surface from the grain. Both the grains are very small. So basically, the dust will travel in the diffuse medium in a long time, 10 to 8 years, before to end up in molecular clouds. So in fact, you have a lot of physics there. It's the physics of condensation and nucleation and condensation. This is a very nice kind of physics, which is based mostly on thermodynamics. Okay. Then you have, you come here in the molecular clouds where you are, you can be hidden from the UV light, too much UV light. So you're going to have physics and chemistry. Then this infalling matter will end up naturally in forming the protostars, and these protostars will also naturally, due to the fact that you have to conserve angular momentum, you form disks. And these are indeed observed, beta pictoris. And you know that in beta pictoris, for example, very recently they have been observed the formation of the planet within the disk. So the whole system is, I would say, well known. So you, well known, well, not well known, but known. So you then go here to chemistry and something which I don't like too much, which is called prebiotic chemistry. The astrochemists are very keen to code prebiotic about anything else. So if they find a molecule which contains two atoms of carbon and one of oxygen, and they say, we are already in the prebiotic world. This is completely absurd. Actually, the prebiotic species or molecules should be considered within an environment which is going to be itself prebiotic. Otherwise, it's completely useless. If you imagine to detect a molecule of glycine, for example, in a molecular cloud, well, fine, this has nothing to do with prebioticity. Okay, I mean, it's very far from prebioticity. So then, after that, you know that since you have lots of debris which are staying in this disk, you have comets and asteroids and IDPs, interplanetary dust grains, dust particles, will in fact end up on the planets, and especially on telluric planets. If you are considering gas phase planets, it's probably much less interesting, because when prerequisite for life is to have solid liquid water. So this will be found only on telluric planets. At least you can start then to do what I call photobiotic chemistry and then biochemistry. And I will show you that you can draw a complete, you can close up the cycle and really start to understand what's going on the planet like Earth. The good thing about Earth is that it is at least a place where we know that life has existed, and certainly has started. It's the only planet which is like that. Remember, I put some ideas of the times. This time evolution is in fact very short, but the time evolution for molecules will be quite longer. So the interstellar medium, you can see, for example, that you have different phases, so that you know this quite well. You have diffuse clouds and the dense clouds. I want to give you some interpretation about the diffuse clouds. How can diffuse clouds have anything to do with life? And then I want to show you that it has indeed something to do with life. Diffuse clouds are called like that because, by definition, they have a low density. The temperature of the gas between 30 and 100 K, reasonably low density. They have visual extinction which are very small, between 0 and 0.2, and they will last a long time. This is an image from Marc-Antoine taken by Herschel and the Polaris cloud. And this is strange also to know that this is a kind of historical point, I would say, because this is done by the satellite Herschel. But when you look at these dense clouds like that, what are 68, where you have much colder temperature, much higher density, higher amounts of extinction, then you start to find molecules. I will tell you that here you don't see any molecules. Or if you accept the pH, which are a little bit special, I would say, you don't have molecules, or at least you have some CH+, but not okay. We have really serious molecules, I would say. So indeed, the strange thing about Herschel is that Herschel was absolutely convinced that these clouds here, black clouds that you can see even with your eyes or at least with binoculars, there were in fact holes in the sky. There was no way to know that in fact this cloud is actually full of matter. And if you start looking with the eyes which can see infrared and millimeter emission, then you see plenty of things. So that's just an historical background.
Well, Caroline Herschel was not of that opinion. It was just William Herschel.
William Herschel.
Caroline Herschel.
Okay. Okay, so why do I discuss about the diffuse clouds regarding to the emergence of life? Not the emergence, but the conditions for life. For a very, very simple reason. You know that in the diffuse medium, using UV lines from atoms, I'm talking about atomic clouds in this case, you know that you can deduce what is called depletion patterns from the elements. So first thing is that the elements are known to be to have a certain abundance. So hydrogen and helium are very abundant. Then you fall on oxygen, carbon, nitrogen, sulfur, and then you fall on rock-forming elements. So what is done in this plot is to plot, in fact, on the zero line, this is the abundance of the elements in the interstellar medium respective to the solar abundance. I'm just taking this as an example. And we plot this as here in axis, the condensation temperature. And you see that the elements, the more with the highest condensation temperature will fall down and are completely depleted from the gas phase. You have to be careful because naturally this is the logarithmic scale. So this means that here 90% of the elements are depleted. Here it's 99, and at -3 it's 99.9% of the elements depleted. It turns out that CNOS, which is here, and phosphorus, and including here arsenic. Let's forget about arsenic, but CNOS and P, they are the elements which are not depleted in the gas phase, and it turns out that naturally they are the elements which make DNA. Now, you can always say, well, indeed, you know, probably you have seen this paper in Science 6 months ago, that some people pretend to have synthesized some bacteria with which includes some arsenic in their DNA structure. The idea is just because if you look at the Mendeleev table, phosphorus and arsenic are just above each other, And so they claim to have replaced the phosphorus by arsenic and to make this bridge, called the phosphate or arsenic bridge between two strands of DNA. So the important thing to understand is that actually all rock formings and abundant elements are just lost in the gas phase because they are just forming rocks. And rocks are refractory elements that will never come back to the gas phase to play with different structures, and especially all these molecules here can form very easily, this molecule here, can form very easily hydrides, CH4, NH3, H2O. This was already planned by, given by Vandelius in 1946, and this was indeed observed by. So there is a drawback on this, because this does not give you the real abundance of the elements. You have to be careful, because this is just relative to their own solar abundance. So now if you turn to the same kind of graph, where you see that you have NCO elements, and then you put also the sulfur elements here, arsenic, phosphorus, then SCMG, F3, this is still with the condensation temperature. Yeah, there is one thing, well, we come back on that. You see that if you then now plot them according to their abundance, which is given from their cosmic abundance, which is good in nucleosynthesis in stars, then you see that C, O, N, and S are the only elements which are left in the gas phase, so that these elements, they are forced to react between them. The others, they are just lost in the grains. And there is only one phosphorus, which is an element where chemistry of phosphorus is essentially done in the crust of the Earth. So, for example, if you imagine that bacteria could eat arsenic to make arsenic rich instead of phosphate, you have to remember that arsenic is anyway at an abundance level which is extremely small, and there is actually no chance that life is going to select the smallest thing to enter in the DNA cycle. So this is a very important idea, and I will come back on that a bit later. So then, what about the detection of interstellar molecules? Yeah, I should say one thing also, because I'm giving talks in different departments, and last time I was in the department of solid-state physics, and all the solid-state physicists were shouting at me saying, this is totally crazy, because how come that the carbon is given to have a condensation temperature of 20 degrees, and how come that this carbon, if you take it as a diamond or as a graphite, is not here in this scale, you know? And in fact, it is true that, that's a good remark, but in fact it's true that aging stars, they are sometimes oxygen-rich and sometimes carbon-rich. So when they are oxygen-rich, all the carbon gets into CO, and when they are carbon-rich, all the carbon ends up in pH and so on. Okay? But since oxygen-rich stars are much more abundant than carbon-rich stars, indeed, lots of carbon here is still in the gas field. And this is not surprising. We remind you that carbon is essential for the chemistry of life and the social life. Okay, so then after that, what about interstellar molecules? Well, maybe this is a bit small, but don't worry. You know that when you are talking to radio astronomers, they are always telling you, well, the interstellar chemistry is extremely complex. And in fact, what you see here is that you have about 150 molecules which are detected. Most of them are organic molecules. Most of them are chains. This is more selection effects, because usually you are using the fact that these molecules they behave as dipoles, okay? And so you need, in fact, to have nice dipole in order to be able to measure rotation times. So that's why you have a tendency to detect, for example, very, very long chains, like HC11N, when nobody knows actually if you have, for example, organics which contain, which are symmetric. Because they are just they are still in some. Okay, so one thing that you should remember, and this is extremely, first, organic molecules dominate. Everybody said, oh, look, organic molecules dominate. Well, fine. This is completely normal because carbon, nitrogen, oxygen, and sulfur, they are the only molecules which can react together. The elements which can react together. So you expect organic chemistry even in the interstellar medium. So the second thing is that as soon as you go from 2 to 3 to 4 to 5 to 6 to 7 atoms, you have to really understand that the elements of these molecules, for each time you add one atom, is determined by 1 dex, which means that each time you divide by 10 the number of molecules. So here you are about at a level of 10 minus 12 to 10 minus 15 compared to hydrogen. So within this series of in fact, complex molecules, the fact to have much more complex molecules, you can imagine, for example, that within this kind of chemistry you may develop completely abiotically DNA, or at least RNA. Well, RNA will be so less abundant that the RNA will never be made by this kind of system. So this is quite important. The other thing which is also interesting is that with this, is that people who say that this is complex chemistry, they forget a little bit that in organic chemistry, if you talk to an organic chemist, the chemist will tell you, well, the number of organic molecules can be counted in millions. It's not in billions, it's even in billions. In fact, the organic chemistry gives you a number of molecules which is virtually infinite. This is a very, very big difference with anything you can do using minerals, because the number of minerals existing in nature is no more than 4,000. So that's also a very, very strong point in favor of carbon as the basic blocks of life, because this is extremely important for Darwinian theory, actually, which stipulates that a very, very small change in any kind of property of living systems will, in fact, what is called selection, will in fact allow the branch of life, the tree of life to be rather branched. And then it turns out that this is only possible if you have a continuum of organic species behind. Otherwise, we will never be able, if you have only 4,000 minerals, we will never be able to develop a mineral life. Okay, so that's a very important thing, and we have to see that it is of limited complexity. So where do we get the complex molecules that are needed for making life? So what I want to see here is that interstellar dust grains actually, they become, within molecular cloud, they become covered with volatile icy mantles. And this is the interesting part, naturally, because again, this volatile icy mantle, they represent about 90% of the mass of the grain, naturally, simply because oxygen, carbon, and nitrogen are much more abundant than working minerals. Okay? So you have usually a grain which is made with a silicate core, which is made within the stars. This silicate core can be, in some case, a carbon core, so that's true, if the grain has been made in a carbon-rich star. Then there is some organic compounds I'm going to talk about, and then you have this volatile ice mantle. So, and this is, you see, as you say, quite small, 0.1, 0.2 micron, 0.3 micron, and this is something that can be seen. So, how are you going to observe the molecules in the ice and the molecules in the gas? Well, for the ice, it's pretty restricted, because the problem is that you have a protostar. The protostar is eating a kind of shell of dust. So most of the energy of the protostar, or all the energy of the protostar, is emitted in the UV, visible also in the UV essentially. And so it's transferred to infrared. And so it gives you an enormous source of radiation, infrared radiation. So this infrared radiation is then trapped, is then absorbed within the molecular cloud, and then with the satellite, in this case ISO or FIT there, you can observe absorption bands. I'm going to give you a few examples. You can observe absorption bands and look at the ices that are formed around this time. One of the drawbacks of this method is that you have only about 20 stars which are observed at night, simply because it's extremely difficult to find stars in the good geometry. Okay? In the gas phase, it's completely different. You are going to have lots of sources which are usually molecular hot cores, in which actually grains are dissolving, further dissolving, and then you can observe by inhibition the grains when it's observed only in absorption in the space. Okay. So there's also another drawback about that is that in the gas phase, you can identify molecules extremely precisely and with very, very good sensitivity. When in the infrared, it's much more difficult because the sensitivity is not that high. Okay. So, well, the formation of grains is such a problem, and the formation of the ice is extremely easy, as said on the Earth in 46. If you have oxygen, carbon, and nitrogen free in a reduced atmosphere, which is what is the interstellar medium, you will naturally form hydrogen. So you will naturally form H2O and CH4. Actually, it has been shown that CH4 is in fact much more present as CH3OH, and you will form also NH3. This is a very special thing because if nitrogen ends up in N2, then you are dead for making any kind of interesting pre-reactive chemistry. Because for making chemistry, pre-reactive chemistry, you really need amines and amines, H2 and OH. So you need to have NH3, and indeed you see NH3 in the and another important molecule is CO for two reasons. The first thing is that carbon and oxygen are the most abundant atoms which are present in the gas phase. So it's completely normal that they will form CO. And CO was detected with one of the first molecules detected in the 70s. Actually, the first molecule detected was detected in the visible in 1937, if I remember. It was CH+. Okay. So basically, how do you, what do you see in the infrared? This is a kind of plot which is always fun because it's a real astronomical plot, where you plot the flux here in Jansky from 0.1 to 100, so it's a logarithmic scale, and where you plot here in the logarithmic scale from about 3 microns to 20 microns. So you are in the vibrational spectroscopy. Okay. So for a spectroscopist like me, these things are very surprising because first of all, we always play with wave numbers because it's a much more sensible unit. And we never play with microns. We never play with logarithmic scale. And you have to realize that, in fact, what you see is a kind of black body radiation from the central star. It's not the central star, it's the shell of dust. Okay. And then you see the water ice band here, which is the OH from the water ice band, the OH vibration. Then you have the other OH vibration, which is here, which is the bending mode. Okay. And then you have, for example, the CO2 molecule, which is here, and the CO2 molecule, which is here. This CO2 molecule is the stretching mode. The CO2 molecule is bending mode. So it's the same molecule. And this CO2 molecule was actually discovered by the IRAS satellite in 89, based on measurements from the lab on the ices that was done actually by me during my thesis. And the measurements on IRAS was also done by myself. And this was six years before the discovery of CO2 by ISO, where suddenly everybody said, there is CO2 in the gas phase as well as in the grains. You have to realize that CO2 is a molecule which cannot be formed in the gas phase because it's a molecule which has a very strong barrier of endothermicity. So you cannot form CO2 in the gas phase. So no one else of the gas phase will produce CO2 if you don't have the grain to help. Okay? So actually, it's a little bit trouble to work. You see, for example, that this band is a silicate band. It's SiO stretch. Okay? And that's why we know there are lots of silicates in space. And you see, for example, that you have a little ring here of CH4. Okay? And I would like to stress also the fact that CO2 and CH4, they are completely symmetric molecules, so they have no radio transitions, and you have a lot of CH4 and CO2 in the atmosphere. So it cannot be done from the ground, and it cannot be done using any radio telescope. So that's what the first time they were really observed only in 1986. So that's very recent. Okay, so what about the abundance now? The abundance relative to H2O. H2O is always dominant. You know that, for example, in comets are extremely rich in water. And so, in fact, if you look at the molecules which are made here, which are present, you see that you have H2O, CO2. Well, this black span here indicates that actually you don't have the same, exactly the same amount of molecules observed, but it is always given relative to H2O. So CO2 is an abundant species, CO can be a very abundant species, and more importantly, CH3OH is in fact very important because it's 30% of H2O in regions of high mass star formation. And that's specifically interesting because CH3OH is also very interesting to form some molecules that we present after. NH3 is given here about 5 to 10%. It was still given as an upper limit at the time when it was made by Emmanuel Lacroix, who was my PhD student before. And Emmanuel did not want to accept the idea that this was not really an upper limit, but really the detection. Now it has been remade, and it's well detected. Most of the nitrogen in NH3. Okay, so it's quite easy when with this BitMOB experiment, which actually it's an acronym for interstellar matter, complex organic molecules, interstellar and planetary matter, complex organic molecules. So you have in the vessel, in the vacuum chamber, you have a cold plate, which is cooled down to 10K, which can also be cooled down to 80K, depending on what you want to do. Then you are preparing a mixture of molecules. You put them as a thin films, and then you have a UV lamp to get the photochemistry, and then you will have an idea of what's going on with the infrared spectrometry. So basically, also there is one thing which is nice. Again, this is problem of optics. But since the grains are very much smaller than the wavelength of observation, the grains basically in this molecular clouds can go up to 0.5 micron, and eventually to 1 micron, but they remain small compared to the wavelength, because these wavelengths are between 2 and 10 microns. Then the effects of scattering are not really a problem. So this means that you can compare very easily, that is shown by Emmanuel, you can compare directly the infrared spectroscopy you obtain in the lab with what is observed in space functions. So this experiment is basically here. You have the vacuum chamber here. This vacuum chamber is in fact a clear star which is open. You just flow some liquid lithium or liquid nitrogen, depending on what you want to do. And then you condense the ice in the middle, and you have the lamp, which is the star. There is one thing which is also very extremely important in this case. It's that this lamp is calibrated so that you can accelerate the kinetics of the reactions. And it's done in a way which is well known in the fact that with the flux of the lamp, basically 1 week in the laboratory is equivalent to about 1 million years in space, the space where it is observed. So actually, you can speed up the grain reaction mechanisms, and this is very interesting because at the end I will show you what kind of method it gives. So basically, you follow this kind of scheme. If you do photochemistry on an ice which is cold, then you are going to build a kind of network of reaction which is so complicated that there is no way to say, to drive all the reactions apart. This is a little bit like Wheeler's experiment, which is a very surprising experiment in a sense, because when Wheeler did this experiment in 1953, he got a lot of chemical species at the end, especially all these amino acids, and Wheeler spent all his life trying to understand the different chemical parts that you have in this kind of reactions. Now you can talk to any kind of photochemist and organic chemist. If you ask him what's going on if I make a mixture of 4 different molecules and I shine UV on it, then he says, well, forget it, it's so complicated that you will never succeed to understand what's going on. So we have decided to work at the end only on the organic residue, which is produced when you end up, at the end of the experiment, you are forced to stop the experiment. Okay? So you stop the experiment, and you end up with an organic residue at 300 K, which can be analyzed by a lot of methods which have nothing to do with astrophysics, and which are the methods that are used in chemistry, especially gas phase chromatography, liquid phase chromatography, and lots of different methods so that you can establish what kind of chemistry you have. And indeed, this chemistry is very interesting, even if it cannot be completely understood and is not totally approached by completely reductionist method. I'm going to show you that. So the idea is to study this organic residue, which is about 1/10,000 in mass of the initial molecules you have put there. So the first thing you have to be careful is that, does it work? I mean, is it astrophysically relevant? Well, this is a spectrum of the source, which is called AJ7009S, where you see that the waterized band is extremely absorbed. Okay, so this is the free micron band, which you can see. The CO2 band is extremely absorbed too. The CO band is well absorbed here. You have a lot of CO. Then you have this W. This is mostly due to CH3OH. Okay, you have CH4, which is there. And CH4, which is observed here. Then you have a silicate band that we don't reproduce in our experiments. We are now reproducing also the silicate band, but this is the mode of the slide. And you have also, for example, one thing which was really, which is very interesting, is OCN minus here, because you have in these reaction channels the possibility to make acido-basic reactions between signmates, actually. And then you make NH4 plus OCN minus. And so the idea is, let's study these organic residue to see if there is the possibility to use them as a template of what's going on in the interstellar medium. So you need to compare with some observations. This is a little bit elaborated, complicated. First of all, in one object, which is called W33A, it has been possible to subtract the spectrum of CH3OH. CH3OH is quite abundant in this source. It has been possible to subtract water and CH3OH from the spectrum, and you end up then with this absorption, which indeed is due in the lab, this is laboratory, this is astrophysical spectrum, which is due to NH4+. One of the reasons why it is difficult is that when you are observing from within the molecular cloud, then you see the cold part of the molecular cloud before you go to the warmer part, which is inside. Okay, so all the absorptions that you can have within the inside of the cloud cannot be really observed. So there is one example, which is monocellulose R2, where you see, this is again the astrospectrum. You see, in fact, that the waterized band, the orange waterized band, in a state which is very special, it's a crystalline state. You see, instead of having this band which is amorphous, you have, in fact, this you're starting to make a crystalline band, and this means, in fact, that the ice is evaporating exactly like that you have in the lab. When you stop the experiment, you evaporate, and so you will see the ice becoming crystalline. And so here, at 3 temperatures, you start evaporating the ice, and at the end, you end up with NH4 plus and OCN minus. And fortunately, in monocellulose R2, you are able to identify NH4 plus here, NH4 plus here, and OCN minus here. So in fact, and NH4 plus here. So in fact, you know that these processes are present in the interstellar medium. So indeed, you have perfect right to study the template you have in your lab. Just saying, well, okay, this template is present on interstellar medium. Okay? So that's one way. So we have done other things, which sometimes are a bit more tricky. We compared also the spectrum of one object. I don't remember which one is that, but this is again a protostar. They are all protostars, where you see the astronomical spectrum, okay, and the spectrum you can produce in the lab, okay, and we try to understand what kind of molecules you have in these absorptions. So you will see, for example, formaldehyde. Okay, it's difficult to know if there are formaldehyde here. You see, for example, formaldehyde and urea. So we published a paper with some people in Marseille about the tentative detection of formaldehyde and urea. Formaldehyde and urea are very, very important pre-biological materials. Okay. So indeed, what was done later by Michel Grévaux, also one of my former student, was to study this organic residue as a template, and we did isolate glycolic acid, hydroacetamide, urea, glycerol, glycerol acid, and glycerolamide. So first of all, most of these molecules, the 6 molecules here, are detected in comets. Comets are the line of possible detection of molecules. So all these molecules are detected in comets. And there is another one thing which is interesting, is that urea and glycolic acid can give you a molecule which is called idantoin, which is present here, if they react together. So actually what we did is that knowing that, I did not know this at the beginning because I'm not an organic chemist, I just learned it by accident. And I say, well, if urea and glycolic acid react, they will form idantoin. Can we find idantoin in our samples? I will show you that it is possible. So before we go further, what about the organic residue? The organic residue, you see, now we are in a real world spectroscopy where we are using wave numbers. So here, this is the 3 micron region, and this is the 5 to 8 micron region. Okay, so you have nice carboxylic acid bands here. You have carbon chains here, CH2, CH3. And then in this region, you have a lot of aliphatics, nitriles, esters, amides, amines. And you have actually a very, very, very complex picture of a macromolecule made by a macromolecule. I should have said a macromolecule. There are more than one macromolecule inside. But it is a very, very sturdy material, which is a little bit yellow. It's very nice when it is yellow because one of the first time when we saw that this was yellow, we said, well, it's full of peptidic bonds. The peptidic bonds give you a yellow color. So it's interesting to know that these materials can have chains of molecules, which are actually representing very interesting stuff for pre-biological materials. One molecule, there is only one molecule which can be detected here. That was done in 1904 by some astrophysicists, by the way, at NASA Ames. Is the molecule which is called HMT, hexamethylene tetramine, which is CH12N4, which is a cage molecule. So indeed, this molecule is one of the molecules which we try to look at the interstellar medium. It's impossible to do it with microwave spectroscopy because it's again a symmetric molecule. And anyway, I will show you that I'm not a very good chemist because I didn't realize that HMT is a very stable molecule if you talk about photochemistry. Usually when I'm doing this chemistry, I'm always trying to relate this to things that I can understand basically. So I looked in the bibliography, what is the use of HMT? You know, the only producer of HMT in the world are the Chinese. I don't know why they are the Chinese, but actually you can buy it by the kilo. It's produced by tons. Okay? And it is used in paints to protect outside paints against the sun. Right? So I was very happy to say, well, okay, this molecule is extremely resistant to UV light. Then one day I realized that HMT was also used as a drug. Okay? And if it is used as a drug, this means that if you put it in water, it's going to be soluble in water. And actually, I did not realize this, and it's going to decompose. And actually, HMT is decomposing in NH3 and H2CO, so it is used as a drug because H2CO is a very good antiseptic. Okay? So, and I did this later on. I said, wow, there is a problem with HMT, and I realized that HMT was not a very stable molecule. As soon as you are in a liquid phase, naturally, in the interstellar medium, you don't care because you never have any liquid phase. Okay? So, why do I say that? Simply because if we claim that photochemistry of ice molecules in space, the interstellar medium, is entering the solar system and brings you photochemical products, then you should find HMT where? You should find HMT in meteorites. Okay? So we looked at this is the GCMS, but it's only the research impact. GCMS, you see the sign of HMT here. This is the HMT we have put in the system. And then when you look in orbit, Asphere and GRA, which is an Antarctica meteorite, we did not detect any orbit, HMT, even in orbit, which is one of the most primitive bodies in the solar system. So we were a bit disappointed until I realized that putting myself HMT in the conditions of extraction of the organic residues in water from the meteorite, putting HMT inside the system, the loss of HMT will be detected. So that's one. We have not yet proven that HMT was present in this meteorite. I was in London 2 days ago, and actually Mark Sefton, an expert in meteorite, told me that I should not choose these meteorites because they have seen liquid water in space, and so I should use other meteorites to do the same operation. So, what about inotoin? So inotoin, in fact, was found. I'm sorry. I'm missing one. Right. Okay. Okay. For inotoin, I will come back on it after. So you have to remember now that when you take these organic residues, these residues, they are consisting of macromolecules. So when you are a chemist, to study a macromolecule, usually you cut it in parts. So you hydrolyze the molecule by putting it in liquid in HCl for a certain time, 100 degrees for about 3 hours, 6 moles of HCl. And naturally, this was done by Milos-Caro, Bernstein, and then by Nuevo with slightly different conditions. We end up with many amino acids. You see the glycine, you see the alanine here, you see the serine, you see decarboxylic acid also, DAP, DAH, and altogether there were about 16 amino acids within this kind of blue. The first, for a French time, it's funny because the first amino acid which is coming here, you see the time, the first amino acid is SAR, which means it's called sarcosine. That's a French thing, but I couldn't believe it when I saw this first thing, the first peak, not a chemist, so they are already this first peak, and so we looked at the table and so it's sarcosine. So that was really funny. But okay. To give you another idea, we made a big sandwich, what we call sandwich sample. The problem is that these organic residues, they are completely made, they are made in the lab. It's a very painful process to make. Basically, you need a good week of experiment to make a very small amount of it. So with my student, Pierre Marcelus, we decided to make a huge sample for about 2 months, working 2 months on it. And so we send it to Colin-Meinert and Nuno Regeneration List, where we are doing double GCMS. So the GCMS is a kind of separation of the components, okay? And one problem you have with GCMS is that very often you have elutions of many different analytes at the same point, okay? So if you are using a double column, then you are able to take away all the co-elutants, and you have only one elutant per peak. So now, up to now, we have detected 27 amino acids, and Colby called me last week saying that she had 29, and then Nuno called me saying, well, we will publish this when we have 40 amino acids. So we still have to wait a few weeks to have these 40 amino acids. And yet, basically, the idea is to compare them strictly with amino acids within meteorites to see if there is the same kind of distribution. So now, let's go to chiral molecules, which is probably the most exciting results we've got recently. So you know maybe what is a chiral molecule, so I'm going just to say it back. The chiral molecule is a molecule which contains a carbon which is asymmetric. An asymmetric carbon is clearly speaking, carbon has 4 valence. Okay, so you have, if you put 4 different chemical subgroups here, you have something which is asymmetric. Asymmetric means that you cannot superimpose 2 molecules Okay, and in fact, they can be superimposed within a mirror image. So that's what it's called. That's why you have, in fact, the idea that care means, in Greek, means hand. Okay? So this chirality comes from the idea that you compare your right hand with your left hand. Okay? And so, one thing which is extremely important to know is that when you have an energomeric excess, this means simply that you have a little bit more of one molecule, L, let's say L for the left and D for the right. Okay? And when you have a racemic mixture, you have exactly the same number of left and right molecules. And if you have an excess, it's different from zero. So why is it important in life? You have the 20 proteinaceous amino acids. Okay? Glycine is not racemic, it's the only one. All the others are it's not chiral, but all the others are chiral. So you know that abiotic amino acids are racemic. Okay? So, for example, when you produce them in photochemistry, you produce always a racemic mixture. Okay? If you look at the biological amino acids, forming proteins, okay, then they are not racemic, but they are homochiral. Homochiral means that they are all of only one sort. It's left. Okay? And it is extremely important because, in fact, if you look at the structure of proteins, it's impossible to imagine that you can produce the structure of proteins using mixtures of racemic amino acids. You need to have them in one form only, either L or so it's important because there is no theory of why this is like that. Why do we have L amino acids in our body, as we said? And there is one thing which is interesting is that when you are looking at the amino acids from meteorites, because there are a lot of amino acids in meteorites, all amino acids measured have an excess in L, not in D. So that's interesting because it suggests, in fact, that when you introduce amino acids on the Earth, you introduce them with an excess. But still, nobody knows why the excess of amino acids is L on the Earth.
Could you just cover the definition of L versus D? Is it the rotation?
Yeah, that comes there. Yeah. Absolutely. So it is an old idea, the interaction of asymmetric light with chiral molecules. Because it was discovered in 1837 by French. The optical activity, which is also called the rotatory power of the chiral molecule. What does it indeed does it mean? You take natural light, which is not polarized, you polarize the it with the polarizer, and you get the polarized light, which is linearly polarized light. Okay? And it turns out that if you go in a medium, which is made of chiral molecules. Now, in this case, L or right, that's what you want to do. Then you make the plane of polarization turning. So, in fact, the electric vector passing through this medium will start to turn to the left or to the right, okay, depending on what kind of molecules you have. So, this is called a rotatory power. So, basically, the idea of the experiment that I'm going to show you now is to do exactly the opposite, is to take a circularly polarized light and see when you are going through a medium which is chiral, you should see if you can select molecules by the left or by the right position. So this was done, actually. It was proposed, in fact, by Meyer-Wenberg in 2001, and it took me about 10 years before to have one result. Now we have two results, but I'll show you the first one. So in fact, we use the same mid-mode experiment, which is a chiral system. So it's the same clear star. And all this is going to be transported on a synchrotron radiation because we need synchrotron radiation to make this kind of experiments. You need a source of synchrotron light and a source of UV-CPL, which is not so easy to make. Okay? So synchrotron radiation, as soon as you do that, you are like an astronomer, you go on big machines, you have to ask for time, you have to ask for beam lines, you have to ask, it's a very complicated stuff. So the whole experiment is then engaged in this synchrotron radiation facility, and usually that's one of the drawbacks also of the method, is that the access to a beamline is not as you can do in your lab. So in my lab I can work 365 days a year. In this case I have 10 days per year, so that's a bit difficult, especially because in 10 days everything should work fine. So very often in 10 days you will have a high probability that something goes wrong. So these are not easy experiments. Okay, so then the experiment is made using two LCDs, air and carbon RCPL, LCPL, and LPL. You can use also the second light to use linearly polarized light. Why do we do that? Simply because we expect that if we are using air light or L light, two different LCDs, then you will select the molecules on the left or on the right. And then you are using the linearly polarized light because you want, with the linearly polarized light, you want your sample to remain fascinating. Okay? So does this work? So ceramic mode is now on the sample porcelain. It's even worse than it was before on Lure. It's even more difficult to install it. And it's a lot of stuff I won't comment. So basically, you are shining your sample, and you are shining the sample exactly. One of the important things is that you are using the same sample that you have been doing with UV photochemistry. So that's important because you are producing the same molecule. And then after that, you are taking the sample out. So you see, this is my student at my technician. We are using, usually, we are doing this cleanly. We are chemists, so at least we have to do gloves, baths, and that. But we are not good chemists, but we are good physicists. So instead of using carbon-12, we are using CH3OH, carbon-13. So in this case, what you are going to analyze is only carbon-13 amino acids. Okay? And in this case, carbon-14 amino acid should be absolutely additive, okay? To the level of 5%. Okay? So, and it works very well indeed. So the result is this one. You see first the idea of still using the GCMS, double GCMS, and you have indeed, so the double GCMS is nice because it can really takes out all the small peaks and the noise here and gives you something which is very, very nice to be able to obtain in antimaterial excess, which are anyway small. I mean, you don't expect to have homochirality from one day to the other. So if you are using LCPL, LPL, or RCPL, then you are producing an excess, which is in this case minus 1.3%, 0% about, and plus 0.7%. With RCPL, LPL, and LCPL, and the error bars 3 sigma are quite significant. So, in fact, you should say, okay, this is nice, but what about 1% if homochirality is 100%? First of all, it turns out, I think this is measured in alanine. It turns out that the excess of L in alanine in meteorites is exactly minus 1.4%. It's maybe complete coincidence, but at least we are giving numbers which are in fact present in meteorites. And the second thing is that we were a bit disappointed because you see that from minus 1.3 to plus 0.71, since the experiment is strictly symmetric, you should have plus 1.3% here. It is not the case, and we realized that we had some trouble during the experiment, and we are using a certain number of UV photons per molecule. And so actually, the enantiomeric excess we get is proportional to the number of carrier photons which have been put inside the system. So this is a very exciting result because it is now confirmed. We have just redone the experiment, and I will just give you a short idea of what's going on there. So the idea is then you have abiotic synthesis. which goes in the meteoritic matter with some excess of enantiomers. And then you need an amplification processes to get material which is really prevalent. So I will not present this yet in some more clarity because this is work which is now in progress. This is not yet finished, so I don't want to talk about. Now we have to construct a plausible astrophysical scenario. Now, one thing which is extremely interesting is that do we have some UV CPL in space? Because if you don't have UV CPL in space, then the whole thing is useless. Well, indeed, UV CPL has been observed in the Orion Nebula with an helicity of about 17% in the infrared. Actually, you can't look in the UV, but the UV is absorbed. It is the same helicity, that's a very interesting thing, on very large scales compared to a planetary system. So this allows actually a solar nebula to be formed in a region of high mass star formation where UV light exists really as UV CPL to a certain extent. So it is not surprising in this case that you will end up with organisms which have imprinted in them the UV CPL light that we have seen when they were filtered directly on the grains. So this kind of scenario must be checked because that's obviously not enough, I would say, but it's already very tentative. Especially because now we have made different experiments that we will not discuss now. So one thing which is extremely important is that we are using another technique which is called Mandeltov, which is time-of-flight mass spectrometry. We are in fact heating these residues with a laser and looking at the time-of-flight mass spectrometry, and we have very high molecular mass. You see, 2600, and this is so there is no hydrolysis in this case, and you are in fact having the macromolecule, and now we have the results which are published, in which we have molecules of molecular mass as high as 10,000. So in this case, the interesting point is that high mass scale like that, you have something which we are looking inside because these are what could be called protoproteins. So that's very interesting because we are using now HPLC measurements, what's called LCMS, which is liquid chromatography with mass spectrometry behind. And then these are techniques which are used in protein analysis. And the chemist that I contacted about told me right on the spot, these molecules, they look like proteins. So that's, now, they are not, be careful, they are not proteins in the sense that protein is synthesized by a biological process. These are completely adaptive protoproteins. So then after that, one thing which is, I'm going to go a bit further about doubling. Then the next point is the ionized search. We looked again in GCMS, so that is not a GCMS, and we found in our residues, we found inotoin here, and we found inotoin also via mass spectroscopy. So what is the interest of inotoin? What do I do with inotoin? Well, it turns out that inotoin has a very prebiotic significance of importance, as it was shown by Comeras and Langer recently. Inotoin is actually catalyst of the formation of peptides. Okay? So you know, the problem of doing chemistry in water is difficult because when you start to have small peptides in water, when you want to make them as long chains, in order to form long chains, proteins are long chains actually, in order to form long chains, you have to get rid of water, okay? And then if you are in water, it's almost impossible. So you need to have catalytic process to do that. And the catalytic process may come from inotoin as well as it becomes for urea also. So the fact to produce so easily these molecules in interstellar, or let's say analogs of interstellar ice, and the fact that this molecule, for example, in oxygen, is a molecule which is present in meteorites, is extremely interesting because this will bring you on Earth and in the Earth ocean something which is able to catalyze the formation of protoproteins. And I'm going to go a little bit on these things as I should mention here. Is it a way to PNAs? PNAs, these are peptidic nucleic acids, which are in fact nucleic acids bound by peptidic bonds. So then in this case, we see that we tend to form something which is looking like an RNA, but naturally not with the phosphate bridges, which have to come somewhere. And then you have to know that these PNAs, they are called autocatalytic molecules, which can be autotrophic, which means in fact that you can select one of the DNA in an environment where you have lots of organic molecules, and these molecules are able not only to autocatalyze themselves, but they can eat everything around them to just make an autocatalytic system. And for physicists, and I'm staying on the physics, this is just what we can call minimal life. I'm going to give you the idea of what is a real minimal life. Just to check this now, is that it's possible, in fact, by doing experiments in the lab, in test tubes, to go to an autocatalytic system, which is the definition for the minimal life. Okay, so to finish this, I made this morning something about what I believe can be done in the lab compared to what cannot be done in the lab. So this is what the title of my book. From astrochemistry to astrobiology, a few speculations. You have here the timeline, okay, where the Earth was born 4.556 billion years. So very often people, or at least when I'm talking to students, they don't understand why we are spending lots of efforts to have the third digit here. Because they always believe this is just due to the sensitivity of some kind of measuring techniques. This may be true, I mean, the measuring techniques are good, but in fact it doesn't mean this at all. It means that the Earth was formed right away. The Earth was formed in a time which is smaller than this number 6. Okay, so that's a very important thing. In fact, the solar system and the planets of the solar system have been born extremely fast, and that's one of the things. So you can define this time scale, you see, from 4.556 to 3.8 billion years. Okay, so you have first astrochemistry, where you have the interstellar ice evolutions to organic matter. Right? Well, this starts about 8 billion years ago, because you have enough. You have to push this back in the cosmic. On the cosmic scale, you have enough carbon, nitrogen, and oxygen to have the same kind of chemistry about 8 billion years ago. Why do I put this? This has nothing to do with the Earth, actually, but this has to do with the formation of exoplanets. Okay? So this means that all this process of life-forming systems, they can be already present in many other planets. Right? That's why I put this. Okay, from astrochemistry, you go to cosmochemistry. Cosmochemistry is the physics of the solar nebula, where in fact you end up with asteroids and comets, and this become meteorites when you find the meteorites on the ground, when you know there is a lot of organic matter in meteorites. Right? Then after that you go to prebiotic chemistry. What is prebiotic chemistry? Prebiotic chemistry is in the primitive Earth oceans, where you have oligopeptides formation, and you are starting to form the protoproteins. Okay? And then you go to something which I call protobiotic chemistry, where you have what is called the PNA world. So for those who know a little bit of the prebiotic systems, you know that actually we are stuck to the RNA world. This is the last hypothesis, which was in 1995, that the first auto-replicating molecule should be the RNA. But if you look at the RNA as a molecule, immediately you are throwing your arms like that, because it's impossible to form by any kind of abiotic experiment RNA. that's clear. There is a missing link in between. Okay, and so this RNA already contains a genetic code. Okay, so in fact, you need to have a way to be able to go to something which is already autocatalytic. So this is what was proposed, the PNA world, where you have autocatalytic, autotrophic molecules, which is the minimal life as defined by physicists. So this means that these molecules, they have functions. Phenolphthalein as a function is a catalyst of molecular. You have the problem of activation. Then, in this case, nobody knows how you can activate these oligonucleotides to be autocatalytic. So this is one of the problems we want to tackle with rebarbaronate, actually, just right now, is to see how we can activate it. And then you have the replication that we did. Replication is naturally completely due to this autocatalytic system. And in this case, you will rebound to the RNA world, where I put here this big black wall, which is the wall of emergence. I believe that you can do all these experiments in the test tube and to go to a minimal life, which is the minimal life for a physicist. Okay, I'm not stupid to consider that I could be a biologist. All right. Behind this wall of emergence, emergence is a word which is really hated by physicists. You know, nobody likes very much the word of emergence because, in principle, this means that you cannot bring reductions through this barrier. So that's the problem which is still there. So in the RNA world, you have minimal life, which is from the biologists. So then after that, you have the Darwinian evolution and life. Okay? There is no Darwinian evolution before this time. And in this case, probably all have heard that we have a common ancestor, which is in fact the last universal common ancestor, which is probably something like the molecule of the RNA world. So I say that, as in computer science, I say Luca 0.1, but there is probably here a Luca 0.0, which has to be found. And this one can be found in the lab, can be made in the laboratory. And so that's very exciting stuff. In fact, because for years, when I was talking on astrobiology with biochemists, I was stuck with this idea that it was impossible to go even there, but in fact, I believe it is possible. So basically, I would like to end up by looking at these non-directed laboratory experiments. What does it mean, non-directed laboratory experiments? If you look at Miller's, results, in fact, one of the problems that Miller got is that after having done his experiments, he was very well celebrated, and Miller went on trying to understand what happened in these experiments. And this was a big disaster because everybody, you have to put this in a historical perspective. 2 weeks before the paper of Miller, a very important paper was published, the one from Watson and Crick about the DNA structure. And it was admitted in this biological community that from Miller experiments to the building up of the DNA of Crick and Watson, that it was just a problem of doing experiments and just it was a small reductionist gap. And actually, it's not a reductionist gap, it's an enormous gap. It's a gap because essentially DNA is a structure which is already totally biological. And so biology is only considered, it's for biologists, the problem of the origin of life does not exist because it's the egg and the chicken. There is absolutely no way to get out of this. Okay? So, in fact, this importance of non-directed experiments is that you let go the experiments, essentially because on the Earth there were no chemists at the time. Now, this is an important thing that apparently nobody has really never understood, in the sense that if you pretend that there was a chemist at the time, then probably you pretend that you are a creationist. So you have to be careful with that. So the idea is to use non-directed experiments, which means that in fact you are simulating the Earth conditions at the beginning, and then you take this material which is of cosmic nature, and you mix them together, and you hope, but be careful, you hope that you are, it's not the actual experiment, but you can facilitate the direction of the experiment. And you hope that you are, you will get one of these PNA, which with some autocatalytic activity. Okay? There is one problem there when you do that, and it's written here, maybe not, there is an open question here. How much time do you need for that? So you know that when the Earth was starting to cool, there was suddenly water. I mean, the first big water condenses at about 4.2 billion years. And, yes, something like 4.2 billion years. And then the life apparently appears at 3.8 billion years. So you have about 400 million years where nothing happened. So you can imagine that you are not going to do an experiment in 400 million years. That's at least. So you need to find a way to accelerate the time. So either there is a hope to do it, so you have to be clever. We are trying to devise an idea about that, but this is not yet right, I would say. Or there is maybe a problem that you have a phase transition. Maybe it's possible that an autocatalytic system is coming within a phase transition. In this case, if this can be shown in the lab, then it will be very easy because phase transition is something which is on the snap. You don't have to wait for 100 million. So this is in the line of what we are trying to do in the laboratory. So that's basically, I want to find essentially Mayo Bender, who was my PhD advisor a very long time ago. And naturally, we'd like to find also Kobayashi, because he was actually the editor of astrobiology, and he had already referred this paper on urea and glycolic acid, and he just sent me a mail saying, have you ever thought about inventorying? And so I started to work on inventorying, and I had this nice and I must say that I must thank the place who gave me money for 10 years without any result for 10 years. The last year was the last year when they told me, this is the last year we fund you, after that you have no result, you quit. So, now they restart from me. Okay, so I give you just one nice slide, which is the UV line from the synchrotron Soleil, which is seen because it goes to an argon filter, xenon filter, and so you get a resonance line because of the xenon which falls in the visible. So this is the only nice thing you can see in this experiment. But okay. Thank you. Yeah.
Why are you sure that the probiotic life or physicist life occurred on the Earth as opposed to in liquid water within a meteorite?
No, it is true that liquid water has been in meteorites. I mean, I'm not talking about when they are there. I'm talking when they were set in the sun. For example, Orgueil is the rock of Orgueil is extremely hydrated, okay? And it can be hydrated only by liquid water. So actually, if you look at the problem, it's pretty simple. You have also to remember that the elements in Orgueil are exactly the same as the sun. Okay? And, they are on the same abundance in the sun. So in fact, Orgueil represents something which has really condensed out of this material, which formed everything, in fact, and has not evolved much. So why I've been with lots of liquid water is essentially it's reasonably well known. It's because there was inside a lot of extinct radionuclides, in 26 especially, probably from supernova explosion not far away. And then it turns out that you had reasonable temperatures to have liquid water within the system for about 1 million years. So that's the point. Life cannot develop at all in a so short time. And so it's very clear. In fact, one thing is that I give here the impression that life is probably very banal. It's very, you have life everywhere. But in fact, it's untrue. If you look at what happened to life after its birth, then you end up looking at the case of Venus or the case of Mars. bit closer to the sun, it's an inferno. Mars is a bit further away, it's freezing like mad. And so there is no life in both these worlds. Okay? So basically, the constraints that are brought by the planetary conditions are extremely important to determine if life is going to stay on it. Okay?
Yeah, but I have to weigh that the lack of likelihood of life developing in that million years against the
it's not even
difficulty of getting high circular polarization in UV, which sounds very, very high. So if you had the PNA auto
in my scheme, the PNA are made on the Earth, they are not made in the meteorite.
I know, but I'm wondering if you can situate that back in the meteorite so that you have a means for self-selection of one of the two.
Yeah, but wait a minute. I made a shortcut here. It turns out that in the in this forest of peaks here, it turns out that now we have detected 40 molecules actually, and it turns out that one of them is a PNA. Okay? So that's in a sample which is made in the lab. Okay? It's a sample which is made in the ice form. Okay? It's warmed up at room temperature, never sees any water. Then the sample is hydrolyzed, cut in pieces in a sense. And it turns out that one of these molecules is a PNA. So that's very exciting stuff. In a sense, we have to be careful because it's a PNA, and we know that the PNA has a faculty of being able to auto-replicate. But absolutely nobody knows how. That's the first thing that you should remember. Since about, I think, 1995, this story of PNAs is in the chemical literature, and everybody is trying to look at the conditions in which you could make a PNA suddenly duplicating itself and eating everything around it. I mean, it has not been observed. That's very sure. So all these ideas that I was transmitting is on the Earth, and the Earth's oceans, and not in the meteorite. That's very clear.
Just because of the time scale.
Yes. Yeah, mostly because of the time scale, and also probably because you need, you have to be careful when you say that you have water in the water phase in the rocks, okay? It's not very clear on which form this water was, okay? The water was certainly partially liquid, partially gas phase, microbubbles, and it was not like in the ocean where you have a pool of water which is much more efficient for bringing molecules together. So that's one of the ideas. But in fact, for the PNA, it doesn't matter so much. The PNA is not such a surprising molecule. It's a known class of PNAs actually. So it's not such a surprising molecule. In autism, for example, you have a few PNAs as molecules. Let's just say that.
So are you saying that the origin of chirality is solved, basically, or are you saying
the origin of
chirality is solved? Are you saying that
no.
Circular polarized UV light, then it's solved.
Then it's solved?
Yes, but
okay.
It is clear. No, you are completely right. There is one thing which is interesting. These experiments, one of the problems is that they are known to do, they are complicated. They are also known to check because you have to redo experiments. So it's never very easy to obtain given time just to redo the experiment. It's a lot of intricate things. But one thing that we have made recently, and which is extremely interesting indeed, is that first we are detecting the electromagnetic excess on alanine, okay? And so the referee of the paper says, well, alanine, what about, okay? In fact, it's a method. We are using the GCMS and we are detecting alanine, and that's it. In fact, the chiral asymmetry is buried in this macromolecule. It's present in the macromolecule. So what we have done recently is that we have irradiated an ice, pure ice. We have irradiated an ice with linearly polarized ice. Okay, we have warmed up the sample, and then when the sample was in the form of disorganic residue, we shined it, UV sprayed on it, and then we obtained a very much higher enantiomeric excess on the system directly. And this matched a very nice principle, which is called the principle of Curie's principle, actually, which says that asymmetric light can transfer its asymmetry on the carbon system. And the best thing is in our case, since we start with ice, the ice is Akira. Okay? So when I was proposed to do this experiment, they went back, called me and said, well, we should do this experiment. So I visited him, discussed with him, and he had his assistant with him, and then his assistant came to me after the big discussion and told me, oh, really, Mayo is crazy, it's never going to work because the ice molecules at the origin are Akira. And so I told him, well, I'm almost sure that in your ice you are forming amino acids. These are Kiras, and then in this case, if you leave enough time to the experiment, these amino acids will see the light, the light, and turn to have a enantiomeric solution. And so I said, okay, I do the experiment anyway, and it's worked. Thank you.